You are watching the Geek Nerder podcast, and we are here to make you curious and inspire you with our deep tech talks on distributed systems, databases, stream processing, and general software engineering. Now sit back and enjoy the episode. Hello, everyone. I am back with another very interesting topic and interesting episode. I have Dhruba, who is the co-founder and CTO at Rockset, and we are going to talk about real-time analytics, search, and how does it work, its internals, its architecture, and the future of search and real-time analytics, and some of the bottlenecks that we see with the existing solutions and limitations of existing solutions. So, Dhruba, it's a pleasure to have you here with me today, and I'm really excited to learn more about Rockset and that domain in general. So let's start with a little bit of introduction about yourself, what you do, a little bit about your background. I know you used to work at Facebook. You were the creator of RocksDB, which is like one of the, like it's a backbone of today's distributed systems, like many of those distributed systems. And you have some major contribution in the Hadoop ecosystem, like HDFS, HBase, and all of that. So tell me about your journey and how did you end up building Rockset?
Cool. Hey, thank you. Hey, KV, good to meet you. And thanks for inviting me to your podcast. Really excited to be here. A short introduction about myself. I'm currently the co founder at Rockset. It's a search database that we can talk about more today. But I've mostly been building like storage and servers and these kind of systems. Prior to Rockset, I was at Facebook when Meta used to be called Facebook. I built a lot of backend systems like photo storage and message backends, including one open source piece of software which is called RocksDB, which is widely used nowadays, which is great. But prior to Facebook, I was at Yahoo, where I built a lot of Hadoop file system. It was the time when Hadoop was very big, like 2006, 2007, and that kind of time frame. And before that, I was at Symantec and some other storage systems and file system companies. So I've been in this area for a long time. I'm excited to talk to you more about what's happening today versus what happened 20 years back.
Awesome. Yeah, it's a pleasure. And I guess Hadoop is still a big thing in some of the companies I have been like
Oh, yeah.
they've
Even
been
in
using.
Meta,
Yeah. Oh, nice.
even in Meta, they use a lot of Hadoop still, but the cloud companies have moved on to do things like Rockset and other
Yeah,
stuff.
yeah,
So
yeah. Awesome. Let's talk about it. So I want to start with a little bit about the historical context. So when you were starting to build Rockset, and what were the existing solutions that you compared, and what were the problem that you were trying to solve?
okay, yeah. Let me think. Let me explain to you the kind of the software ecosystem at that time, right?
Hmm.
So we were at Facebook, and the challenge there was that a lot of things were about scale, right? It's easy, like I keep saying, it's easy to build infrastructure when it is few machines. Building infrastructure challenge usually comes when we are talking about scale, right?
Yeah.
And so at Facebook, what happened was that there were a lot of applications that needed to operate on data very quickly, right? Take, for
Hmm.
example, spam detection, right? So Facebook, people post some kinds of URLs that not supposed to be shared, like illegal websites or stuff like that. So the goal for that system was to figure out how quickly can we quarantine these bad posts.
Hmm.
Same thing with Facebook's whole revenue model is advertisement based, right? So when a customer or when a user logs into the Facebook web or a mobile page, how can you show him the most relevant ads to the person? So ad serving. And these kind of systems, if you see them, they're all the basic requirement is obviously very large scale. And the second requirement is that it needs to be very fast and quick. So you can't be waiting for some results to appear on your application, right? When you swipe an application, you just need to see the ads. So that's the part where real time became very important. And then as you see, all of these are search systems, right? You have millions of ads in your repository. Which one to pick based on the user's profile? So it's a search database that we needed. So essentially what I saw is that from the Hadoop world, which was very much batch and analytical and reporting frameworks, Facebook tried to move to more real time so that they can get more engagement. So and that time, that was the genesis of this change, right? This like applications became more and more real time, fundamental to latencies. That's one. And the second one that I did see is that compute architectures have also evolved,
Hmm.
right? Previously, people used to store data on disks and like hard disks and whatever else, but then memory started to become cheaper, SSDs became cheaper. So you had a combination of hardware changes that were happening and the requirements of the application to be more real time and fast. This was early on, like early 2010s, 2011, 12, when Facebook went public at that time. But I had seen this now going even further speed for the last 10 years or so. So this is the background when we started off Rockset back in 2017. The premise was that how can you build a search database which is optimized for real time? There are other applications, of course, there are a lot of homegrown solutions out there. But like I said, the challenge is usually to build software systems at scale or like backend systems at scale. And so our focus was entirely performance, price, and ability to scale to large backend databases. So that was the ecosystem at that time.
So whenever I think about systems that are working with a lot of data, with a variety of data, so I keep thinking about these three V's. I don't know where I read. So it's variety of data, it's velocity, and the volume. And whenever
Mhm.
these three are like really high, probably we need a like a more sophisticated and specialized solution, probably like Rockset.
Yes. Sometimes you don't need to have all the three. Sometimes you probably need a combination of just two to
Yeah.
make your systems not be price performant unless you get a top of the line cutting edge software. If your data is coming in very fast, which is the velocity part, you need to be able to make sure that you can process them and get your queries done in time. If you're just talking about like the total amount of data set, like the volume, without having the velocity and the variety, then maybe Hadoop like systems are fine because you're just storing them, right? You're not processing them much.
Yeah.
So, yeah, I think it's a combination of these three that has happened in the recent past. The
Interesting.
variety, I think, is super important because back in 5 years ago, people talked about JSON and semi structured data, right?
Yeah.
But now in the last 1 year, you'd see a lot of vector data, which is what I mean by the variety is constantly changing, what type of data you want to store and how you want to process it.
Yeah, that's definitely interesting. So Rockset is a search and real-time analytics database. But what does it mean when we say search and real-time? Because I see these terms are really overloaded and different people use it in different contexts. So I want our viewers to take this in the right direction and understand the true meaning when we say search and real-time analytics. So when I think about search, I like based on my experience, I typically think of like full text search and solutions like Elasticsearch, and real time also means different things for different people. So how would you define search and real time analytics database?
Yeah, sometimes it means slightly different things to different people. So let me dissect all the three things you mentioned, right? You mentioned real time, you mentioned search, and you mentioned analytics. So the real time part is a little bit easier to explain because what happens is that when somebody says, I'm a real time database, that basically means that your queries are fast, which basically is an interactive, it's a customer facing application that you are powering, or you are powering a data app that has a few milliseconds of data latency for queries, right? So the real time part is that the queries have to be fast, but also that the data that your system is producing, let's say you have a bunch of sensors in your trucks, right? You're a truck service and every truck is producing a sensor. How quickly can you use that sensor event to make decisions in your analytical work? So that's the data latency. We talk about query latency and we talk about data latency. So for real time, many applications need both. They need fast data latency and fast query latency. Sometimes real time applications just need fast query latency. They don't really care even if the data is 10 minutes old. So that's the real time part of systems, right? When we talk about real time. But coming back to search and analytics, what has happened is that over time, analytics started. When you talk about analytics, you are talking about analyzing data, right? Just think about the human perception. When you say analyze, it's not like something you need to do quickly. You need to usually think and like ruminate and like kind of understand what how to make sense out of this data. So that's called analysis. So analysis typically started with very batch systems. Like Hadoop was a very good example. A lot of warehouses like Snowflake or Redshift, whatever else you use, those are all mostly started from batch system, which is where analytics started. But when you talk about search, think about it, right? Oh, I lost my pen. Let me search for it. The whole focus is how quickly can I find this so that I can get on with my work. You see what I'm saying? So
Yeah.
the search systems typically are low latency things, which is not like a batch process. It's about finding the right thing at the right instant and making sense out of it. Like the Facebook ad placement or the spam detection examples I gave you, those are all search based systems because you can't wait for something to happen and analyze for 100 hours before deciding what to do. So this is the intersection between search and real time analytics. So Rockset, what it supports is that it's a database that is very much focused on the search kind of angle, which are vector search, data search, keyword search, text search, geo search. People are looking for ships in a certain geolocation, let's say. So that's a geo search query. All of these are search, which is all focused on low latency applications. But then you can also do more real time analytics, which is about, let's say, well, take for example, a personalization system or a recommendation system that also needs some amount of analysis to happen as part of your search query. So this is where the search and the real time analytics come together to give you the new age requirements that most applications have. Am I able to explain this to you?
Absolutely. I think this is a very good mental model to understand like both the things. As you mentioned, search is usually you want quick results. And analytics may mean you may want to analyze data, which may take like maybe minutes, hours, days, depending on the use case. But then when you add the real time aspect of it, it brings in the freshness of data and also the speed of queries that you want to serve your data and results. So I think that's a good mental model, and I'm going to use it to explain this to others as well. Thank you. Uh, Coming to the Elasticsearch point, right? So I used to work with an architect, and we built this application. We used Elasticsearch to provide search on different types of data. Specifically, it was full text search, and we wanted to serve, user facing workload backed by Elasticsearch, and that usually had problems like ingestion was slow and query latency were used to also there was spiky behavior. So, what is different? Like when I talk about search in real time, probably in many cases, Elasticsearch will also just do fine. So, I guess the scale aspect of it makes the real difference, as you mentioned earlier. So, what is the limitation in Elasticsearch that Rockset aims to solve?
Yeah, great question. So again, Elasticsearch has been around for a long time. So it's a great piece of software. Just off the bat, it uses something called Lucene as its storage engine, and Lucene started in like 1999 or something, right? So just imagine how long it has been.
Yeah.
But over time, what has happened is that all of these systems were built when the cloud did not exist. So with the advent of the cloud, you could continue to run Elasticsearch. It will still work, but essentially you are not leveraging the power of the cloud. And I can explain what those things are to make your systems better, right? So Elasticsearch also will scale to large sizes. You have hundreds of terabytes of data. You can store them in Elastic. But the challenge is that in the cloud, the hardware is fluid, which basically means that you can get new machines at the call of an API. You don't have to set up a data center and put new machines, right? So that flexibility is what Elasticsearch is not leveraging, and I'll explain how, right? So in Rockset, what has happened? The basic reason people prefer Rockset to Elastic is that we have something called compute separation, which basically means that compute and storage are separated out. So you store the data on a set of machines and you use your compute for queries on a different set of machines. And then the reason, so this is done usually on the cloud systems because you could provision these machines using APIs. And depending on how much data you want to store, you can get more machines to store your data. But if you have small size of data and you have a lot of queries, you can provision more machines for your compute so that your queries are faster. And so because these are disaggregated, you get a great price performance compared to Elasticsearch. That's the first one. And the other reason, relatedly, is that you can have different compute instances in Rockset serving the same storage. So think about how you do it in Elastic, right? You store data in Elastic, you make 3 replicas of data. for durability reasons. And then your compute or query for Elastic is together with your storage. Whereas in Rockset, you store data with one replica because you use the cloud S3 and other blob storage for durability. And then if you have multiple applications querying the same data, you just spin up more and more compute units and it queries the same data set. So just imagine in Elastic, you'd have to make multiple copies of your Elasticsearch cluster to solve different applications. In Rockset, you don't need to do that. So this is what I mean by it's cloud friendly. And the second thing that people mostly prefer us is that Rockset has a converged index built in. I can explain more later, but converged index essentially lets you make search queries and it also makes you make analytical queries together in one system. So Elastic, it's difficult to do because you do mostly search queries, but then if you also need a little bit of aggregations and analytics, you have to write some of the code yourself. So that's another difference. And the third difference is that Rockset is standard SQL. Now, it could mean a lot of things. Some people like SQL, some people might not like it. But so Rockset is a SQL system, but you can also write REST APIs. So the power of SQL is that you can join two data sets. Whereas in Elastic, if you have to join two data sets, you have to go to a lot of hooplas in your application to get joins correctly. There's a SQL interface to Elastic, but it doesn't really do joins. And in my terminology, SQL is SQL with joins. If somebody says, I do SQL and I only do select star, that anybody can do this, right? So Rockset is a very powerful SQL system. You can join multiple data sets together. And this is one big difference from Elastic. So those are the two or three big differences compared to Elastic, is how Rockset is designed and architected today.
Very, very interesting. And we are going to talk about the compute storage separation and also compute, and also converged index and so many interesting things a bit later. But that is a good summary of why Elasticsearch wouldn't work, especially when it comes to the cloud environments. When I initially learned about Elasticsearch, it was, you know, the feature itself was meant to be elastic, as in machines can go on and off, and the overall workload is elastic. You can scale up and scale down, and depending on that. But with the more advent of new technologies in the cloud domain, and your workload has also changing, the expectations from the user has also changed. I think something like Rockset makes sense because it specializes in that kind of area.
Yeah, no, I think you were right. I mean, Elasticsearch also, please don't get me wrong. You could add machines to the cluster, you could delete machines, but usually people do that once a month. You cannot do it for every minute or every second. You
Yeah,
see what I'm saying? So that's what I mean by the cloud elasticity is not there. There is
yeah.
elasticity in Elastic, but typical people provision 100 machines today and then they'll add 10 machines every month or things like those. Whereas in Rockset, you don't have to do anything. You could add two machines every 2 minutes to increase your backend and then decrease it when there is no work left to be done. So this is why you get great price performance. Yeah, yeah. So
I
that's
think
how.
so. That's a great point, and thanks for sharing that. Let's start with understanding at a high level how does Rockset's architecture look like? So, what are the key components involved? So, you mentioned there's storage, there's compute, there's API layer, there's also SQL support. So, if I have to look at from a very high level perspective, what kind of components would I look at when I talk about Rockset's
Sure, yeah,
architecture?
absolutely, yeah. Let me try to explain it bottom up, right? Because it's easier to explain.
Hmm.
So obviously, all data. So Rockset is a cloud system, which basically means that you can run it on any of the clouds, which essentially means that Rockset gets data durability by storing data in cloud storage.
Hmm.
So you don't have to provision disks or machines or saying that, okay, cloud storage is very flexible, right? You just store data and cloud can take it. So the durability of your data when you put to Rockset is based on cloud storage. And then we have a hot storage layer, which is essentially a cache of all the data that you have in your cloud storage. It's an SSD based layer. The reason, again, we have an SSD based layer for storing all your data is not for durability. Durability is maintained by cloud storage, but the SSD layer is mostly for performance. So we have one replica of data in this SSD layer. So that's your hot storage layer. So that's the second part. And then the third part is our compute and memory that is used to serve queries. This is what we call as the virtual instance, a Rockset virtual instance. It's a virtual instance is actually a cluster of machines. It's a cluster of machines which has compute and memory together. And so this virtual instance is what runs your queries. It's a virtual instance is what takes in new data and does the indexing at the time and stores it in storage. So essentially, there are three layers in the software hierarchy, right? So you have a virtual instance, we have hot storage, and we have cloud storage. That's the hardware centric perspective I gave you, right? Because I'm talking about how hardware is laid out. But if you're looking at software, how the software architecture of Rockset is, for software, we have an architecture which we call the ALT architecture, aggregator leaf tailor architecture, where it essentially means that when data comes in, we index this data. So Rockset is very much an indexing engine at scale. So it indexes this data, and that indexing is done by a set of compute nodes that is just doing indexing. It's not doing querying, it's not doing anything else. So it's indexing, and then it goes to the leaves. The leaves are the guys who are storing the data in SSDs. We use RocksDB, which is an open source database, for storing this data. And then we have aggregators, which are used for querying this data. And aggregators are another set of virtual instances or compute nodes that serve the queries, the SQL queries. So the benefit of having these three parts in a software architecture is that if there is more data to store, then you just make more of the leaves scale up. If you have more incoming data, like you said, the velocity of data is very high, then you just scale up your ingest nodes and then they index more without having to scale up the storage nodes and the query nodes. And then if suddenly you have a burst of queries, then you just scale up your query nodes, which are the aggregators, and you don't have to scale up the ingesters or the storage system. So this is why this is ideal for real time, because in real time, there is new data coming in, your data never stops, and your queries never stop. That's the kind of one sweeping statement about most real time systems. And to handle these real time workloads, you need a separation of ingest compute, storage, and query compute separated out. This is another difference from Elastic. It's not really separated out there. Whereas in Rockset, if you start ingesting a lot of data, it doesn't impact your queries because you have a separate set of compute nodes. So that's the software architecture mapped to the hardware that I explained earlier. Does it
Yeah,
resonate with you?
I think so. I have some clarity around that. It's still a bit blurry, so I would love to go deeper and make it more clear. So, if I understand correctly, there are three layers, as you mentioned. One is the, let's say, object store, for example, S3, where you store the data. Then there's the hot storage layer, which is based on the SSD. It uses RocksDB and it stores data. And then there is the compute nodes, which takes care of ingestion and indexing and all of that, and also queries. And there's also a separation between the ingestion nodes and the query nodes, and there's also separation between the storage and compute nodes. So there is like different types of separations we are talking about here. There's one point that you mentioned. Of course, since you have these three layers separately, you can scale them differently. Like for, let's say, object store, you don't have to think about it because the cloud provider takes care of the durability part of it. The storage node that you have, the hot storage one, you can scale that separately as well, and depending on what exactly you're doing. So my question is, if I have a lot of data ingestion happening, I can of course scale the ingestion nodes, which is the compute node, which is, let's say, stateless. But doesn't that impact this hot storage node as well? So how do we separate that out? So whenever I have scaling out of compute nodes, I don't have to worry about the impact that it could make on the hot storage nodes.
Great question. Fantastic. So let me explain that and peel one more layer on this stack. So the hot storage layer are essentially, so all of these layers are essentially Kubernetes based clusters. Okay, so you can think about the hot storage layer as one deployment in Kubernetes. You can talk about the ingest layer as another deployment in a Kubernetes system. So what happens is that the hot storage layers, let's say the hot storage layer has 10 machines, and every machine has a bunch of SSDs associated with it. These are locally attached SSDs. And let's say that every SSD is 80% full, right? So now a customer comes in and says, okay, I'm going to ingest 100 terabytes of data from some external system and index it and start serving queries. It's a new app that they're onboarding. So what will happen is that the user will say, okay, ingest data from this data source, index it. The fact that you're doing it automatically tells our system that, okay, I'm going to index 100 terabytes of data. So I probably need whatever 100 terabytes of SSD storage in the next few minutes or maybe an hour or so. And so what it will do is that it will expand the hot storage layer from 10 machines to, let's say, 15 machines. And this is like a consistent ring that we use to place. These are SSD files that are spread along all these nodes. And we will rehash some of this based on the consistent hashing and then migrate some of these files to other machines, the newly allocated machines, and spread out the load among all the machines in your cluster. The reason this is easy to do is because this is all RocksDB files. So these are SSD files, so sorted files on disk. And the key benefit from RocksDB is that RocksDB is a log structured merge database, which basically means that it never updates a file in place. Updates to a record always happens to a new file on storage. So once you have an SSD file, it's very easy to replicate it or reduce replicas or whatever else, or move it, migrate from one storage machine to another, because it doesn't change. It's a read-only system, most of it, right? So this is the beauty of an LSM system. Again, there are other LSM systems as well, but for RocksDB, what happens is that we have tons of, let's say you have a 100 terabyte RocksDB database, right? 99.9 terabytes is read-only. It's only the new writes that are happening are getting flushed to new files on storage. But it's very easy to rebalance the 99.9 terabytes of data because that's all read-only files. The way we rebalance the hot storage tier, coming back to your question, is that we add a few more machines based on the capacity requirements automatically. The customer doesn't have to do anything. And then our consistent hashing ring automatically moves some data from existing machines to these new machines. And then the new data that you are ingesting, 100 terabytes, gets spread out among all the shards you have in this cluster. So the beauty of this is that you get the bandwidth of the entire cluster for your workload because they're spread out among all the SSDs. And these are locally attached SSDs, which give you so much better kind of latencies compared to EBS or compared to other systems that some other solutions might have. But yeah, this is how the rebalancing happens. The rebalancing happens when you ingest new data to Rockset.
That makes sense. That is so interesting. You talked about some of the very interesting concepts when it comes to distributed system, like the LSM tree, the SST tables that you have, and then the consistent hashing algorithm. So basically, it helps you to avoid like moving all the data. Since you're hashing it consistently, you only have to move partial data so you can grow nicely. And then the LSM, the amazing fact that you mentioned that it is not mutated. So the data is immutable, which means that you can just move that data file to a different location without worrying that it could be mutated and you would lose that state. That does make sense, and that probably makes it easier, as you mentioned. How is the data partitioned though? Is it based on, so let's take an example here. So let's say I have an e-commerce application and I have, I don't know, product catalog and user click stream and different types of data coming in. And I want to ingest this data to be able to search and provide real-time analytics features. So how does the partition happen, and what do you need from the user's perspective? Like from as a developer, what do I define that, okay, this is how I want to partition my data, and how does that work?
Got it. Yeah. So you asked about partitionability of the data, but I also thought maybe I'll explain a little bit about your previous thing where you talked about mutability of data. You talked about the mutability of records as well. So Rockset is actually a fully mutable system, which basically means that if you have a record, let's say just like Postgres from that instance, right? You have a record with a primary key and you can update any field in the record at any time. But inside Rockset, we use RocksDB, and RocksDB, what it does is that it keeps versions of these files, and each of these files are read-only files. So from the internals of RocksDB, the files are not mutable, but from the application's perspective, when you're using Rockset, you can have a fully mutable record set that you are updating every field on the record. In Rockset, actually, you can update every field, or combinations of fields, because you can, based on a primary key, or you can delete the record, right? So it's a completely just like a Postgres kind of system. So now coming back to the partitionability of data. So take, for example, I'll compare it with familiar systems people have. People might be using a warehouse, let's say Snowflake or some other Redshift kind of warehouses, where when data comes in, they usually partition it by day or by hour, right? You store different partitions in your backend system. Whereas in Rockset, you don't have to partition this data upfront. Think about it, right? Think about a MySQL or a Postgres database. You don't really partition this data. The concept of partition doesn't appear because it's one gigantic database. So Rockset is very similar to this, is that internally there are shards of your data set. And we basically take the primary key of your record and then hash it to one of the nodes in the backend. This is, again, it's not visible to the user, but internally, if you inspect how the engine works, you open the car and you see how is the engine working inside. What you would see is that it's a document sharded system, which basically means that when you get a document, you hash the document based on the primary key or anything else you can specify. And the entire document gets stored in one of the machines in the backend. So this is the reason why you can have a very high velocity update rate, because every document is hashing to a different number. And so if your cluster is 100 nodes, it randomly goes to one of the nodes in the cluster. You see how I'm saying? So you can essentially use all the 100 nodes to keep indexing. So it's spray out all your data. So the concept of partitioning is there internally, but the customer doesn't have to do it. So it's document sharded. And then the interesting part is that because it's document sharded, when a query comes in, the query also cannot leverage a partition, and it goes to all the nodes in the cluster. So every query needs to fan out to all the machines in the cluster, do some work, whatever local work. Let's say somebody is looking for hello string, the word in some data set. So every node is going to do the searching in his local pieces of data and give you results back, and the results are sorted and gives back to the user. Now, the beauty of this solution is that if you're 100 machines, so one single query can use all the compute of your entire cluster. You see what I'm saying?
Yeah.
Whereas when you partition it, let's say if your partition is based on some IDs and your query comes in, you send the query to that partition only, and only the CPUs on that partition can work on the data set. So our system, Rockset, is optimized for latency. It's like Google search, right? Google search systems, you have to scale, but your queries have to be in like whatever, 20 milliseconds. You can't have a batch system. So the whole point of these search databases like Rockset and Google search was one of the first fundamental ones, is that you spray out all your data to all your machines. And then when queries come in, you spray that query to all the nodes in your cluster. Do local computation, because then you can leverage thousands of compute for the single query and then return results back. And this is traditionally very different from warehouses and systems where they're very much partitioned, and it was mostly optimized for throughput. All the previous systems that you have mentioned, the kind of systems optimized for throughput, whereas for Rockset, it's optimized for latency. And it's also optimized for throughput, but the first primary citizen is how can you make sure that the latency of your query is the smallest, and then we try to optimize for throughput and other things. But that's a perception that, or the perspective is that, yes, if you need low latency queries, you need a search database. You can't do a partitioned warehouse type of thing to, say, power your customer facing analytical applications, because those could become slow.
Very interesting. So basically, there is no problem of hot partitioning because a user just selected a key which is not distributed evenly, and then you end up putting all the queries to a single node, which becomes a hot partition depending on the data. So that kind of problem is not there.
I mean, I think the problem is lessened to a great degree, right? The problem is always there in some sense, because depending on your hashing algorithms, maybe there is one node which has more work to be done versus the other nodes. So when a query comes in, let's say you have 100 machines, but it's not 1% work being done in every of the 100 machines. There could be some imbalance. But my point, I think, is that it's far better system for balancing compared to a partition system where there'll always be imbalance.
That's a
So
good
yeah,
point.
so keeping systems balanced, I think hashing typically works, and you can also pick different hashing algorithms or different keys in your input record to hash, so that you can get a very well behaved system. So typically, what we see in production is that when our queries come in, all the nodes in our cluster are equally used, which is a good thing. But there are slight ups and downs compared from node to node.
Interesting. That's a good point. Practically, things can happen, but the probability of it happening is very low. And even if it happens, the system can self heal itself by, let's say,
Yes.
repartitioning or rehashing. Okay, interesting. So I think my understanding is a bit more clear, but I want to go a bit more deeper to understand how things are working. So there's a ingestion happening. There are compute node specific for ingestion. There is hot storage. There is object store. What is the difference? So I understand object store is pretty cheap when it comes to storing a ton of data, but it's slow in terms of latency. And then you have hot storage. The name is itself is hot, that you're serving hot queries. So how does the database decide how much data to keep in the hot storage and how much data to keep only in object store? And how does that decision making and communication happens between hot storage and the object store?
Got it. Yeah, that's a great point. So there are essentially three levels of cache in our system. So let me explain the caching hierarchy. Then it's easy to explain what gets stored where.
Yeah.
So we have these virtual instances, which is compute and cache. So virtual instances are where the compute is running, where your queries are getting served. And it runs RocksDB again, and RocksDB has something called a block cache, which is essentially stored in the compute's memory, RAM associated with the memory. So that's the first level of cache, which is closest to the application. Then comes the hot storage layer. Oh, okay. So the compute's cache is based on block sizes of RocksDB. So the cache is not like whole files. It's 16K or whatever, 8K blocks that you are. So the hottest blocks are what is cached closest to the compute. The hot storage layer is essentially a file cache. It's not a block cache. So it caches entire files from object store into the hot storage layer. It makes sense so far?
Yeah.
So all your data is in is in cloud storage in the form of cloud storage files. Some of it or most of it is cached in the hot storage layer as files, as entire files. And then based on your application access patterns, blocks of these files are cached closest to the compute, which is called the virtual instance. So typically in production, what happens is that most of our customers have applications which are customer facing applications, which basically means that they cannot afford to make queries say longer than whatever 200 milliseconds or 100 milliseconds. But so this is the reason why most of our customers prefer to keep all their files on hot storage, because for cloud storage what happens is that the P99 latency on cloud storage is like 400 500 milliseconds. So if you don't have some blocks in your hot storage layer, once a while you will see your queries to be taking like a second. And most of our customers don't want it. So what they do is that they say, yeah, put all the files in hot storage. But the working set that fits in the virtual instance cache, that's what essentially the hottest of the hot. Those are blocks. Those are close to the compute. And these are the like the three hierarchies that we have. But now there is also ways where you can say that, oh, I have this data set that I'm not going to use for some time, so don't put it in hot storage, and so it goes only to cloud storage. That's possible, but it's mostly not really serving real-time apps at that time. So like I said, 99.9% of all our customers put all their data in hot storage. It's still very price performant because we do use different levels of compression. We do delta encoding between keys. We make sure that there's only one replica in hot storage, because unlike say Elastic or whatever Druid and other systems that are out there, we don't have to make replicas of this data. So just imagine if you compare it to an existing Elasticsearch system where you have three replicas of data for durability. Just by the fact that we have one replica means that we are already like 2-3 times more efficient for price performance. So this is And that's the reason why most customers actually prefer to put all their data in hot storage.
Okay. That makes sense. So basically, the object store is mainly for durability and to save some
Correct.
cost. If
Correct.
I have the use case where, okay, slightly greater latencies are fine, then I can choose to offload some of the storage to object store and save some money. And hot storage is typically used for performance, like high latency, low latency applications, as you mentioned, like less than 200 milliseconds. And there's like a hard limit on how much you can go when it comes to latency. So then people can choose to use the hot storage only and not use the object store. Is that correct?
Yes. No, so absolutely. So again, there's nothing architecturally preventing us from doing exactly what you said.
Hmm.
But what we typically do is that in the interest that we get the right use cases for Rockset, we try to make sure we put in a few limits for us. Take, for example, the default query timeout is 2 minutes. So we don't want any batch queries to be running in Rockset. It's a SQL system, so sometimes people in the early days we saw that they're not using us for the right use cases. They're running some SQL queries which go for 10 minutes. So we said, okay, we are going to put a hard limit. The query limits is 2 minute timeout. You can extend it. They can talk to customer support and we can set it larger. But by default, it's a 2 minute query latency. Similarly, by default, all data resides in hot storage because our focus is to get use cases which are very low latency, real time, customer facing use cases. But yes, what you are absolutely right. There are provisions for us where you can say that I don't want to make any queries on this data set, so just put it in cold store. And so then it's just in cold store. So that feature is there.
Awesome. Whenever we talk about this real time analytics and you want analytics, so you're interested in a lot of data, but when I talk about one record, only a few columns. Typically, systems use a column format storage. How does storage look like in Rockset?
Okay. Yeah, I can tell you a little bit about the converged index things, right? So this is an invention that you have which talks about putting different types of indices together into one piece of software called the converged index. So what are these different indices that we have? So let me start off with, say, an inverted index, which is what, say, Elasticsearch has. People might be familiar with Elasticsearch. So that's one kind of indexing where you have an inverted index. Another kind of indexing could be a geo index because it's like GPS locations and you want to build an index for this. The new kinds of indexing is a vector search index. So again, just yet another data type for us. So we have a data type called vectors. Just like you have integers, strings, whatever, now we have a new data type called vectors, and we index all the vectors together. And then columnar storage, like you said, traditionally for large scans, you need column storage. So that's a column index. So we put, and then the range indexes. Let's say you have a field which is an integer. You want to create some indices based on the range of the integer so that you can find your queries fast. So all these indices is what we call is a converged index, and it's built by default for you. So again, you can switch it off. You can say, I don't want indexing on these fields, blah, blah, blah. But the default is that out of the box, you get performance where all your query, all your fields are indexed. So this is extremely appealing to a lot of application developers because just think about how you would do it on, say, Postgres, right? You create a column, you create a field with 500, create a record with 500 fields, and then your application changes. Now you have to go back to the database administrator, say, hey, create an index on this column. And then after 2 weeks, you need to build another application. You go back to your administrator saying, hey, create another index on this column. This problem doesn't happen on Rockset because we have leveraged RocksDB to reduce the cost of indexing so much that you can afford to index all these fields at scale. Again, this is optional. You could switch it off if you don't like this or you think it is too much. You don't really need to index everything. So this is where our storage format is. So the storage format is built on RocksDB. RocksDB has keys and values internally. And for Rockset, the data model is that you send JSON type of documents, right? If you're familiar with MongoDB, it's a JSON database. You can think about Rockset as something very similar. You can put semi-structured data into Rockset. Rockset will take each of the fields in your document and index every field, including nested fields, arrays, and stuff like that. And then when you make queries through standard SQL, the queries will automatically figure out which index to use. You can again override some of these by using hints and other things in the queries, but by default, the cost-based optimizer that you have as part of the SQL engine is supposed to leverage the storage format, which is we know which indexes are built and how it is built, and leverage those indexes to make your queries faster. So yeah, the storage format is a RocksDB based format. It's immutable records that you have, and it builds all kinds of indices to make your queries faster without you as a user having to figure out which indices to build and which indices to use as part of the queries. Both of those are transparent. Over time, what has happened is that when you go back to our customers and ask us, what's the best reason that you like Rockset? The most common answer that we get now is that, oh, you reduced my 1 year of development time to 1 week, something like this, because of some of these automatic things that happen for you. You can always make these things better by switching off indices and providing hints in your queries. But the default out of the box experience is that it lets developers move really fast in building their applications.
That does make a lot of sense. Since we are talking about indexes, I want to make our viewers aware that there is a conference organized by Rockset on 16th May called Index 2024. So you will see the link here, and I'll also add it in the YouTube description. So please register and attend the conference. And there's an amazing lineup of speakers and amazing talks available. So please go and register and check it out.
Yeah, the conference has great speakers from a lot of our colleagues and compatriots, right? Things you great you'd hear great talks from Netflix on how to do personalization, for example. Then you hear from Matthias, who is the founder of the FACE system. FACE is like the Facebook simulator search algorithms. So he's going to speak about the design of how FACE started. So we talk a lot about vector search there. You'd also hear from Uber, again, large systems at scaling systems, and you'll also hear what those companies are doing to address these kind of search systems at scale. So it's not a Rockset conference; it's a very community-focused conference. So if you come and attend it, you will hear people using different software stacks to solve search at scale. So that's the focus of the conference.
Awesome. Coming back to the indexing point, right? I have some questions there. So it's amazing that Rockset would automatically create different types of indexes for me. And I, as a developer user, I don't have to think about, oh, I need this index or that index. And then database, like creating indexes on a live database is always challenging. You gave example of Postgres, and you have to think about what kind of index you are going to create and could it impact the live workload and all of that.
Right.
So it's always a pain. So I would love to have my data indexed already. But whenever I think about those many indexes created, I always think about the right amplification, cost amplification, and all of that. So how is that taken care by Rockset?
The ability to automatically keep indexing new fields that are appearing in your database. Now, in Postgres, you can't have this. So the ability that we have compute separation actually allows us to keep indexing data on like hundreds of fields per record without impacting your queries. When you're talking about, oh yeah, and the other part is we do have ability to create indices only when you want to. Take for example vectors, right? You want to build a similarity search index for vectors using face, for example. So how Rockset does is that you can say create similarity index. So it is there exists a command to create an index specifically. It basically creates a course index of all your data. You can continue to do updates, and those updates show up in your queries. But the course index doesn't need to be rebuilt continuously because it's again a similarity search characteristic that you can afford to build the course index, let's say once every day or once every 2 days. And that similarity search index is built only when the customer requests it to be built, or you can set a scheduled policy saying that build this index once every 2 days. Again, to reduce cost or to trade off recall versus the CPU that you spend in building the index. So that's the part of separating out the indexing compute from the query compute. And the second part that you asked is that how do you make this price performant efficient or at least economically feasible is how I talk about it, customers. So there are two ways you do this. The default is that we build indices on all the columns of your data set. But there are use cases where when you're talking about hundreds of terabytes or 500 terabytes of data, there is an amplification to building each of the indices and storage amplification. There is less amplification on compute because, like I said, the compute, it's mostly the caching is per blocks of your data in your virtual instance. So as long as you're not using an index, it's not costing you anything on your queries, but it does cost you on storage. Now there are features where you can actually go drop indices on the fly. So you can say that, okay, you can look at all your query logs and you can say that, okay, I'm not really using, excuse me, these 5 indices. So if I'm not using, can I drop all the index? And you can drop it to reduce your storage cost. So that feature is there. The interesting part is that when you drop the index, it needs compute to drop the index, right? Because it needs to go find out what things to remove and get rid of it. That all happens in the ingestion compute unit. And again, coming back to the question, it doesn't impact any of your queries that you are making online. So to summarize, I think we give all the bells and whistles to an application developer to make sure that his or her application is running at best price performance. We also internally we use RocksDB to do this indexing, and RocksDB was built to do indexing at scale at Facebook. So to give you some historical context, Facebook used to have a social graph, right? It has like people and posts that they're making. It's a social graph that's stored in like MySQL system, sharded MySQL system. But then you need to build a secondary index on that humongous social graph. The social graph is like hundreds of terabytes. No, actually, even more now. That social graph, what you need to do is to build a secondary index. For example, when you go visit, say, the Golden Gate Bridge in San Francisco, you want to see who all of your friends have visited the Golden Gate Bridge. So you need an index on the Golden Gate Bridge versus to quickly find out who all of your friends have visited this place. So RocksDB was built to make this secondary index on your social graph. And so the optimizations that have gone into building indexes is tremendous compared to standard systems like SQL or Postgres that people are used to. RocksDB has log structured merge engine. So like I said, when you're building new indices, you don't have to do B tree type of indexing. In MySQL, what happens is that when you update an index, you have to go to a B tree page, read it, and then split the page and then write it to different places if needed. So RocksDB, they don't happen. They write all new writes go to new places, and there's a compaction process that does it. So it changes all random read modify writes to sequential reads and writes, which is a great way to make sure that the cost of indexing is less compared to traditional B tree based systems. So optimizations, essentially what I'm saying is that optimizations have been built from ground up to make sure indexing cost is very less compared to traditional systems. But it would still, sometimes at scale, you still don't want to build indices on some records or some fields, and you can always switch them off. So that's the structure. So we
Yeah.
start from a default where we build all the indices for you. But if you think you need better price performance and don't want to waste some time, you can always go and delete some of the indices you like.
Okay.
See,
Yeah.
the mindset is so different compared to MySQL. MySQL, you build table with no indices. And every index you add, you have to think, oh my goodness, this might cause some trouble to my database. So this is why if you use Rockset, you can move your app, you can write applications very fast and then try to optimize it as and when you go.
Absolutely. That's a great point that you mentioned. In a relational database like Postgres and MySQL, you have to think about, okay, what kind of index you have to create. And then you end up creating some indexes. I mean, different people work on that product over the years, and you see that
Correct.
there's ton of indexes used. Some of them are redundant, and you still have this question like, why this database is not using my index? And there's a lot of
Absolutely.
investigation going on, and it's always the case.
Correct.
So I, as a developer, I think this balance that Rockset provides is pretty good, because I, as a developer, initially I don't have to think about, okay, do I need to create this index or not, and understand the query patterns and if these indexes are used, and probably eventually turn it off if it is not used, right? So I also have that kind of flexibility. So it's pretty good. I think this part I understand pretty well now. Also, the converged index is pretty good. Uh, let's talk a bit about, you know, so you mentioned that there is this mutation happening. So RocksDB is immutable, but Rockset provides this layer of mutability on top, right? Is that understanding correct? So, if so, how does it do that? And what is the use case when it comes to like real time analytics or search that you need mutability?
Got it. Yeah. So let me start off maybe with an example, right? And then see how Rockset can solve this. So let's talk about, let's say, an auction system, like a real-time auction system. So like if you take, for example, one of our big customers is Whatnot, which is doing a real-time auction system. So when you log into Whatnot, you see all the auctions that are relevant to you. So this is personalization, right? You go and you don't want to see auctions in uh, cars if you are interested in, let's say, cricket bats or baseball bats, right? So you need to personalize this based on the user's interest. What the system will do is that it's doing a vector search to find all matching items that can potentially be similar to the ones that your interests are. And then quickly, it also wants to filter out auctions that has expired or that has already been shown by to you. So this is what we call as a hybrid search system. You do a vector search, but then you also need to filter on metadata or
Hmm.
other kinds of metadata to show relevant personalization. So to do this, and then new updates are coming into this data set, right? So auction. So let's say an auction was there, but now the auction has expired. So you need to go update that auction, like expiry time on that auction record, so that new metadata filtering can filter out those records. So if you look at the updates, every record is updatable because what happens is that if the record has 10 fields, each field is stored in a RocksDB key value pair. Think about it. It's not as simple as this, but just to explain, I'm explaining it this way. Let's say you have a record with name, address, and auction expiry date, right? Each of these fields in your record is stored as a key, separate key and value in RocksDB. So now when you want to update the expiry time, you just need to go update one key value in RocksDB internally, and you don't have to reindex the entire system. So this is another big difference from Elastic. So in Elastic, if you update a field, you need to reread and all the fields in a document and reindex them. Again, just architecturally different. Whereas in Rockset, because you use a key value store, you can go update every field in your record, and then all your search queries essentially see this update as soon as it happens, and then show it in your results. Like I gave you the example of Whatnot. And the mutability is super useful for most customers because it's like a deduplication system. So let me explain it to how you would do this on a warehouse. So warehouses like Snowflake and Redshift, typically updates are not what they support at high volume. So what people will do is that if you update, they will actually write a new record with a new, say, auction expiry time. So now every update is a new record in a warehouse. And at query time, you'd have to deduplicate all these records to find out if the auction has actually expired. You see what I'm saying? So let's say the auction, let's say the key is the auction ID. Now you have 10 records, auction ID with different attributes in the fields that are updated. And at query time, to merge all these 10 records and actually find what is the latest state of your auction and then show them. So this deduplication happens at query time for a lot of warehouse kind of applications. It's okay because those are mostly batch applications. Whereas in Rockset, because our focus is low latency queries, we try to do deduplication at write time. And so this is why mutability is super useful for these applications where you don't have to keep multiple versions of the same record. You update things in place and then queries come in and always find the latest version of your record. So yeah, so that's the difference between kind of the requirements of mutability and updates and what RocksDB gives us and how we shred this document into key values in RocksDB.
That is very interesting, and I've seen this happening. As you mentioned, since we cannot mutate, you end up creating new version, and then some of the complexity also is pushed to the application layer, which is, let's say, a workaround, because ultimately your database should solve that in a effective way that works for you. So that's a great feature. Let's talk about the query side of things, right? So I have my data ingested. It's all auto indexed, and the latency is quite good. When I write a query which is pretty heavy, because it's, let's say it's fans out to like each of the nodes. And so what does, like, how does this query reaches the API layer and then goes to the compute node and fetches data from the hot storage? And tell us a bit about that.
Got it. Yeah, that's a great question again. So this is a question that is asked by a lot of our customers also when they start using Rockset. So what happens is that when a query comes in, obviously there's an API layer which does some validation, verification, authentication, permission checking, all that good stuff. And some of those things, after some of those things are happened, we actually compile the query, parse the query, and compile the query. Our backend system that is doing this is all C++, the latest version of C++. So we are optimizing for latency of queries again all the time. What it means is, so this is the reason why we opted not to write some of this code in other interpreted languages versus C++, because we thought we'll get the best performance. So we have built a native SQL engine entirely built on C++ internally at Rockset. It's a distributed SQL engine. So the query compile obviously is not distributed. It's one node which is compiling the query, finding how to compile it. And then every node in your cluster has a process called the leaf aggregator running on each of the nodes. And the query talks to each of these nodes using gRPC. These are communication channels that are pre-established. It's not like you connect and then you send queries. It's all pre-established or pooled. Let me call it pooling. And then the query fragments all are given to all the leaf nodes to execute in parallel. And then it's like a volcano style model where when data is pushed from all the leaf nodes back to the aggregator is just processing them when results are coming back from all the leaf nodes. No JVMs get created or no threads get created. These are all pre-created, again, optimized for like low latency queries. We actually do have a JavaScript UDF. Again, I can talk about how that also runs. You can specify some UDFs as well as part of the query, but assuming there's no UDFs, it all runs in C++. It queries RocksDB. It does the filtering. It does aggregation locally on each of the nodes. Let's say if you're finding the max of a field, every node is going to do the local max and give it back to your aggregator. And the aggregator is going to, so the optimize, there's one more thing that I did not catch here is the optimizer. So when a query comes in, we have a cost-based optimizer, which is essentially looking at statistics of every field in every collection to find out what is the best, which kind of filtering. Should I do the filtering before the sort? Should I do the aggregations before or after? These kind of questions is what it's trying to optimize for. It's very like a Orca style optimizer where we will try to parallelize as much as possible on the leaf nodes, but then some things are not parallelizable. Let's say you're doing maybe like a distinct or whatever, count distincts. And sometimes not everything is parallelizable on all the nodes. So in that case, we do send it to the aggregators. And the aggregators are the ones which are combining the results from all the leaf nodes and giving the replies back to you. A lot of the authentication stuff that I mentioned, right? And the API server layer, that is mostly written in Java because there is authentication, there is permission checking. But once we go to the query level, which is all about bits and bytes and processing bytes of information, that's all at C++.
Okay.
So that's the overall of the query engine.
That makes a lot of sense. So basically, the data movement between the leaf nodes and the aggregator nodes is kept to minimal, because it pushes the what kind of data you want, and that kind of filtering is done at the leaf node itself. So it doesn't have to send that data to aggregator, and then the filtering would happen. So filtering is already done at the leaf node, and aggregator just have to, let's say distinct or counting or summing or whatever. It does that and sends back the result. And I also wanted to ask the communication, but you already mentioned it's a gRPC communication. The connections are pooled. It's already set, established. So this is good. Since you also talked about the SQL support, and you mentioned like what SQL support really means, it's to ability to join, different types of data sets. How does join work in this case, though, in Rockset?
So SQL. So in my definition, a SQL is only when you have SQL with joins. Like I said, there are other data systems that say SQL, but they're not really joins. So I'm discounting them. Joins, I think, are the most powerful thing that SQL have. So we do support different types of joins. Again, the cost-based optimizer, let's say, decide to do a hash join, depending on like your histogram of your data set. But you can always override some of the join strategies and the join policies. The, there's one thing that maybe is different from, say, doing a join in Hadoop or Hive versus Rockset. In batch systems like Hive, the joining process can create a lot of intermediate data sets that get stored in like disks or dumped to disks and then get processed. Whereas at Rockset, we don't dump any of the intermediate transient data sets to storage. It's all memory based. So focused on low latency again. So there's a difference in the type of applications that we want to serve. So if you're familiar with joins in warehouses, joins in Hive, Hadoop, Rockset, or joins work exactly the same way, except that if you have a lot of transient data that your joins are processing, then we would term it as more like a reporting query or a batch query and not really a real-time query. So we don't spill any data to disk as part of the query. We use the VI memory, which is your memory that you have in your virtual instance to cache, to create the temporary data set to serve your joins. And if that's not enough, then we ask you to increase the size of your virtual instance. Let's say, so the virtual instance comes in t-shirt sizes, like you have a small virtual instance, medium, large, XL, and every size that you upgrade to gets twice the amount of memory. So the focus again is that this not again people are usually very familiar with SQL, so they start using our software very quickly. But sometimes if they're talking about large data sets that they need to join, first to tell them that you must be doing a reporting queries, which is okay. You can still do it in Rockset, but you have to do these kind of configs to be able to support large transient, large temporary data sets that are created as part of the join.
Mhm.
But most of the time people don't have to worry about which join strategy is getting used unless you want to override it using a hint. So you can do that. You can do a nested loop join, you can do hack join, broadcast join, whatever else you think is appropriate, but the system is going to pick one for you based on the metrics that or the statistics that Rockset already collects. So the statistics are collected when you're ingesting data as part of the indexing, and the statistics are always up to date, which is a good thing. You don't have to do anything special to build statistics.
Okay.
Does that answer your question?
Yeah, I think it does. And so it's a so basically there is still an option to run reporting style of query.
Yes.
It's just the memory that is used is of the sorry, what node did you mention? The
Yeah.
virtual instance. Sorry, virtual instance that needs to be bumped up if you want to run these kind of queries, and it comes in t-shirt sizes. That makes sense. But what happens to the 2-minute timeout? Do I have to also bump that up?
Great question. You catch me at the right places. So thanks for being so meticulous. This is a really great question. So what happens is that typically for Rockset, people use it for customer facing low latency queries. But then after running this in production for 6 months or a year, they also realize that they also need to run some reports on the same data set. There's reports that might be running on a warehouse earlier, they might be running on some other systems. Then they say that it's easy for me to run Rockset, let me try. So what we do suggest to customers is that they create a separate virtual instance. Because we have compute separation, you don't need to replicate your data. You just create a separate virtual instance and you run your reporting query on that virtual instance. You spin up the virtual instance, run the reporting query for whatever 1 hour, a month, and then shut it down. So the fact that you can do this on the fly with just an API or click of a button means that you get your reports very quickly. You don't spend extra money or anything because you can shut down these virtual instances as soon as you are done, and you don't have to keep it alive for your entire month. And so this is a typical expand use cases for us where people do run some reports. And so for those, as part of so all Rockset queries are SQL queries that come over REST APIs. Everything is a REST API. And the REST API, you can specify the timeout. You can override the default timeout. So we allow overriding default timeout now all the way to 30 minutes. So you can actually run a query that can run for 30 minutes and return you results. So yes. So yeah, people do run those now often, but usually that's not the reason why Rockset is being used by a customer. is the real-time search use cases is where Rockset is mostly being used, and these are expand use cases where people also want to do a few things that are out that they need to do as part of their regular reporting framework.
That does make sense. And I've seen this, and I've also had this temptation like, oh, I have all this data here. Why can't I run a quick reporting here? And
Exactly.
this kind of feature really helps me for those kind of use cases where I have the ability to bump up these virtual instances and run my query, which is reporting style, which is not what my regular workload looks like. And then without impacting the other workload, I can run my reporting queries, which is
Right.
quite nice. I think we have covered high level architecture, we have covered the right path, indexing, the queries, and I think that's a great deep dive into understanding how Rockset works and why it specializes in search and real-time analytics as a database with this amazing SQL support as well, because SQL is everywhere and people need it. That reduces the friction to adopt any new technology because most of the people are familiar with SQL. I want to ask you, what is Rockset not great for? What kind of use cases? So if I have a use case, when should I say that, okay, Rockset is not made for this use case?
Yeah, I think maybe I already provided some tidbits of information, so I'll try to tie up those knots. One is that if you want to run a query which runs for tens of hours or whatever, right? And you have large intermediate data sets that you are talking about. This is like a Hive query. It's maybe a warehouse query that's humongous that goes on for many hours. Those are things that usually not the greatest fit for Rockset. That's one. The second one are things like, again, I think you can run some of these. People do run these things, but maybe not the most ideal. Is like queries that process your entire data set. So typically, search queries they use the index to filter out relevant records of your data set, right? Whereas there might be a query which says that look at all my 100 terabytes of data and count or bucketize each one of them. Let's say a number of people between at age between 1 to 2, 2 to 3, and summarize all my information. So summarization queries probably are not the best things to run on Rockset. Again, it's doable. Like I said, you usually create a separate VI and you run those queries separately so you don't impact production. But it's not something that you would get better price performance compared to running it in a warehouse or compare running it to Hive or some other or EMR.
Awesome. Yeah, that makes sense. One last question about the future. What are the future things coming up in Rockset and probably when as well, if you can share some details there?
Oh, absolutely, absolutely, yeah. We have got real-time analytics use cases very much covered now, which is a good way that customers use us and immediately start getting value. The interesting things that are happening are more on vector search side of things, where we have a lot of customers now demanding and using us for vector searches. So, what are the interesting things we are doing for vector search? So, again, vectors is just yet another data type for us. The reason people like Rockset vector search is because we can do real time updates to vectors. You don't have to rebuild the index again and again. And the same thing, you can have separate virtual instances, one for personalization, one for recommendation, one for fraud detection, and those kind of things. The interesting things that are coming out about Rockset is ability to do billions of vectors at scale. I think you will see something soon enough where you're talking about tens of billions of vectors at scale. I don't think any of the open source vector databases can do that currently. So we will have something there. And we will also have a lot of improvements that are integrations that we are doing with other similarity search engines or similarity search algorithms that you can natively use at Rockset. So that's the focus area for us in the next few months.
Awesome. I'm really looking forward to the amazing features that you guys are soon rolling it out. And I am looking forward to also releasing this episode. Thanks a lot for joining me today, taking the time out to explain all the amazing things. I'm sure it is going to be very interesting for our viewers who want to learn, let's say, about distributed systems, how things are done, how a search and real time analytics database works at such a humongous scale. And yeah, I loved like discussing all the amazing concepts that you've shared. And thanks a lot for joining me today.
I hope to see you in the Index conference, KV, and any of your viewers. So we'll talk a lot about some of these things over there.
Absolutely.
Great.
And if you like this episode, please subscribe to the channel. Also consider subscribing to the Rockset's YouTube channel, where Dhruba shares a lot of whiteboarding sessions and amazing discussions.
Thank you, guys. Thanks a lot. Bye.